We are now recording. Sorry about that. Unmute. Okay, good. All right. Okay, so does anybody have any questions about how I did any of this? All right, so that gets you started. You got to work out the integrals. Have confidence that you can do that, and then when you get stuck, you'll go to, or maybe you won't even get stuck. Maybe you'll just go cheat right away and go to the internet and get the answers. Of course, you might not call it cheating. You might call it being efficient. All right, so that's for 6C. Let's look at 7A. Since we did a polar coordinate yesterday, let's give you a hint on this one. What's our domain that we're interested in? We're interested in this square. Actually, let me do it this way. So we're interested. So what are we interested in? We're interested in the following region. Let's take. We're going from this point to here, and then we're going from this point to here, and this point to here, and then of course, whoop. So this is the guy we're after. We can label a few of these points to make it really clear. So those are the four vertices of our square. Now, you would argue that if the center of mass would be in the middle, but that's not the case here because this thing has density that varies. The density varies. So the mass is going to be the integral from 0, 1 to 0, 1. That's easy because they both go from 0 to 1. And then what is your rho? Well, your rho is 1 plus 1/2 x. And then you could do this either way, dy dx or dx dx. And then, of course, m sub y would be this integral. And it would be x times this. Maybe you just want to do this one dx dy because it's already in x's. These are not complicated integrals. And of course, m sub x would be y times 1 plus 1/2 x. And then you could do this whatever way you want it, dx dy. So maybe we can actually compute these. This is pretty straightforward. This will be, what the heck, why not? Let's compute them. What's this integral? If I integrate with respect to y, I get, you get 1 times y, so 1/2 xy. But when you plug in 1, all you're getting is what you started with. So this just simplifies to 0, 1, 1 plus 1/2 x dx, which is x plus 1/4 x squared from 0 to 1. And so your mass is 5/4. Now, this guy, if I integrate my x first, and please stop me at any time if you have a question. I sometimes forget that you guys don't integrate as much as I do, so maybe you're missing it. So this guy, when I integrate the x, I have an x, so this becomes 1/2 x squared. And then this becomes 1/2, and then with the x squared, so it becomes 1/6 x cubed from 0 to 1, and then this is a dy. So when you plug in 1, you're left with 3/6 and 1/6, which is 4/6. So this just becomes 2/3 the integral from 0 to 1 of dy, and you just get 2/3. Okay, now this one up here, let's branch this off so we don't get all sort of discombobulated with this. All right, so what is this integral? Well, if we integrate the x first, we can write this as the integral from 0 to 1 of y. And then what's this integral? Well, this becomes x plus 1/4 x squared from 0 to 1. And we did this one downstairs. We already did this integral. So this becomes 5/4 the integral from 0 to 1 of y dy. And when you integrate this, you get y squared over 2. So this just becomes 5/8. Again, you might have to verify yourself of all this. It's never a bad thing. It's never a bad thing if you actually do the details here. You might catch a silly error that I made, or maybe not. Okay, so here's what's interesting is we can compute these things. So what do we remember? We divide both of these moments by the mass. That's the definition. So we get the answer is the center of mass is, well, what is x bar? So x bar is m sub y over m. So that's 2/3 over 5/4. That's kind of sloppy. Let's not squeeze it in there like this. I got a better idea. So we'll remember this is m sub y over m, comma, m sub x over m. Let's just do the arithmetic in our head. So what's 2/3 divided by 5/4? That's the same as 2/3 times 4/5. So you get 8 over 15. And then what is 5/8 divided by 5/4? That's 20 over 40. So that's 1/2. And if you ponder this, it should not be shocking that this is in fact the center of mass. Here's a good thing to think about. Notice the density only depend on the x-axis. So that means left and right, which means the density was uniform up and down. So it shouldn't shock you that as far as we're concerned, the center of mass in the y direction would be in the center. So it shouldn't shock you that that's the case. It also shouldn't shock you if you think about how what the density formula tells us is that x moves further away from the origin, we increase our density. So if you imagine, how do you balance something that's not uniform? Would you balance it where it's more dense or less dense? Where would you expect to put it? Well, if you think about 8/15, that is a little bigger than a half, right? So it shouldn't shock you that this center of mass is right in here. It's a little bigger than a half in the x and y direction, but it's exactly a half up and down. Because if you look at the formula for the row, it's telling us we're more dense towards the right side of the square. So we would expect to balance it there. Does anybody have a question about this? All right, so there you go. That's fun. And then I guess I'll let you have the joys of problem 8. Triple integrals. Okay, let's check to see what's happening here. Okay, so what's next? Well, we kind of want to tie all this stuff in a knot before we go any forward. Go forward, I should say. So here's kind of what I'd like to do. I mentioned this at the end of last class, I think, or maybe the middle of last class. So it's an important reminder. Polar. Let me actually say it a little differently. Be very precise. Integration in polar cylindrical in spherical coordinates what is it? I shouldn't say are. I don't know the correct English here. Is it are or is? I guess we'll say is. All this is a generalization of U sub from calculus 1. So let me remind you of what we're doing in that case. So let's recall, this is actually so in Calc 1, when integrating, let's say we were doing the integral from 0 to 1 of, I don't know, 1 plus 3x to the 5th. So in Calc 1, when we were integrating this, what we would do is we would set u equal to 1 plus 3x, and du would be 3 dx. What were we actually doing? Well, you're going from xy coordinates to uy coordinates. That's what you were actually doing. Now, we don't really get in depth in that in Calc 1 because it's, you know, it's one of those things that as an instructor, you kind of, you go in your head, how in depth should we go with this? But typically in Calc 1, we don't state these big scary theorems. We basically just say, here, let you do this, and it works. So let's look at it from a geometric standpoint, if you will. So let's go back a page. What was the original function? Well, the original function was 1 plus 3x to the 5th, say. So what does that graph look like? Well, you know that it's going to be some polynomial and it's going to be steep because it's the fifth power. So if you know, the graph was 1 plus 3x to the fifth. So if we draw a coordinate system here, where's mine? So what I'm going to do is I'm going to draw my XY coordinate system. Now, I'm not going to draw this to scale, but hopefully you get the idea. When I plug in 0, you know, what does this curve look like? Well, let's be very, very specific. So the curve's going to look like this. So this is, again, not going to be to scale, but as soon as you think you've mastered this, you realize you don't. So this is a polynomial, and its graph is going to look like this. Again, and let's put some points in here so you can see what I mean. So this is y equals 1 plus 3x to the fifth. Now, I'm not interested in what happens to the left of 0 or to the right of 1. We know at 1, when I plug in 1, what is this point? Well, this is 4 to the fifth. So what's 4 to the fifth power? Well, if you must, you go to a calculator. And you get that it's 1,024. So this is the point 1, 1,024. Yikes. So this integral that we originally started with, if you want, you can think of it as being the area under this curve. That's what you can think of it as. Now, if we go and do that substitution, what happens when we perform our substitution? Well, we let u equal that creature. So we get, let's change our color. Let's go to green. What does the integral become? Well, if u is that, you end up getting the integral from u to the fifth du. Then you have this 3 floating around. So it would be, you know, if you do your u substitution, what is u? U is, excuse me, what is dx? It's 1/3 du. And then what are your bounds? Well, your new bounds become, when x is 0, what is u? When x is 0, u is 1. And when x is 1, u is 4. That's the integral we get. Okay, so what is that in the other coordinate system? Well, basically we're saying that the two places have the same, or two regions have the same area. Someone has a question? No. Wrong. More than that. So again, now we're integrating from, say, 1 to 4. Oh my God. The moment I think I figured out this drawing stuff, I keep getting. So when I plug this, when I plug in 1, this is 1. And then when I plug in 4, what I'm doing is I'm going like this. So this region under this particular curve, so what's this point? This is the point 4, 1, 0, 2, 4. And this is the point 1, 1. And what is this curve? This is the curve y equals u to the 5th. So this is your u-axis and this is your y-axis. So basically what we're saying is these have the same areas. So if I get my pink, except if you do this thing properly, it's not going to be the same exact area. You have this factor of 1/3. So the blue area is 1/3 the green area. Or I said that incorrectly. I said that incorrectly. 1/3 of the green area is the blue area. So let's be very clear. This is the green region. And this is the blue region. Okay, so anyhow, this is something, well, I should retire from spelling class. Kid can't spell with this little pen. So that integral represents the area of the blue region. On the right, the integral is the green region. And if I divide that area by 3, I get the same thing as the blue region. Does anybody have a question about this picture before we kind of say why it's important? Okay, so that's kind of what we want to say. So this, along with polar, cylindrical, etc., are special cases of what's called change of variables. So we're not going to get into the specifics of this because it's quite a difficult thing, but we can give you sort of a tip of the iceberg so that you can see how to use it. Does anybody have a question right now about any of this? Get my water while you ponder. Okay, so what does this mean in, say, 2D? So So for double integrals, we can change from, say, x and y to new variables u and v. Or from x and y to, say, r and theta. That would be what we did with polar. So the big question is, just like with polar, so when we do this, what happens to dA? So for polar, we know dA equals r dr d theta. But for general dA, what is dx dy in terms of, say, du and dv? I hope you understand what I'm saying here. And if we're changing variables, these quote-unquote differentials, what happens to them? Bless you, even though I didn't hear it. Okay, so what we'd like to do is we'd like to do an I'll give an intuitive argument. Because I think this is the best way to learn it. If you want the details, at least semi-technical, they are in advanced books or the internet. If you want to do that. This Calc 3 is not the place for the advanced details. There's a fair amount of details in the book, but so the key is to always keep the one dimension version in your mind. That's the key. Keep one dimension in your mind. So in R1, dx was equal to something times du. So we should expect dx dy to be something times du dv in R2. And we already saw that with polar coordinates. There was what was that something? That something was r. Now, where did that something come from in Calc 1? That something came from in Calc 1 by setting u to a new function or a new expression. And then when you took the derivative, that's where that something came in. So let's go to the next page and think about that. So in Calc 1 or in R1, you set u equal to some new expression. And that implied that du was just the derivative of that expression, dx. Right? That's what we did. I mean, go back a couple slides. I set my u to be 1 plus, what, was it 3x or something? Yeah, 1 plus 3x. So in R2, we have two expressions. We have a new thing. So let's use, say we use our vector notation, because we're going to take a point in R2 and we're going to assign it to a new point with two expressions. So suppose in R2 we have uv equals two new functions. Maybe I'll use g of, now here's the dilemma. If we're being very careful, what are our expressions going to be of? Our expressions are not going to be just a function of x, but they're going to be perhaps a function of y. But here, we don't have a natural generalization of the derivative. What would it mean to do this? So here's the thing. If we think there's going to be an analogy like there is in R1, where the differential du and dx are going to be related using some derivative. Well, here, what are we going to differentiate? We have g and h, but then we also have two variables, x and y. Clearly, we would expect the partials to be involved, but the question is, how are they involved? How are they involved? So again, if we want to go with the sort of, if we want to go with the generalization of what I have at the top of the screen, I want to write du dv as something. What would it be? So this is you know, again, I'm trying to brainstorm. I'm trying to get you to think about this. I'm not necessarily saying this is easy, because it's really not an easy idea. But we can get some intuition if we think about this. So we know that the partials have to be involved. Now, we have talked about derivatives in many different ways, but one thing we haven't discussed yet, necessarily in general, was how do we deal with the derivative of a function from Rn into Rm? Or for example, in this case, what is our function doing? It's taking two guys and mapping it to two guys. So we have to think about what would possibly be some sort of way of thinking about this that would also, in the case of one dimension, reduce down to what we already know from Calc 1. So let's think about it. We have two functions. We have g and we have h. And each one of those is going to have a partial. So even if we just thought from the beginning, like, okay, that means I'm going to have 4 partial derivatives. So we have 4 things that we think might be useful. What's the best way to align 4 things? Well, I don't know if it's the best way, but what have we done in the past when we've had objects maybe more than 2 or 3? You know, one way we've done this is we've used the idea of a matrix. So what we do here is we define what's called a Jacobian. So that's named after someone, so it's a capital J. What is the Jacobian? So let's be specific now. So to go from xy to uv, we need what's called a map or a function. So we typically call this type of function a map or a transformation. Now, why would we call it a transformation? Well, think real simple geometry. Suppose I have a square sitting in the xy plane and I want to rotate it. Well, there's a very simple way you can describe so that you take each point on that square and you multiply it by something or do something and it rotates the square. Similarly, I might have some object in the plane and I want to move it somewhere or shrink it or make it grow. One way to do that is to multiply those points by something. And so that is a function. So we can think about, we have this new function. We have we'll call it t for transformation. So what does t do? T takes a point and maps it to a new point. So t takes a point x comma y and it assigns it to a new value. What does it assign it to? Well, it assigns it to something g of u comma v and then something else, some other expression, say u comma v, which we'll call h. And so we define the Jacobian as follows. J equals the determinant of a matrix. What is this matrix? Well, we're going to take our partial derivatives. Let's take the partial of x with respect to u, the partial of x with respect to y, and then the partial of y with respect to u. Excuse me, this should be a v up here. Getting ahead of myself. This is the partial with respect to v, and then this is the partial of y with respect to v. Yikes. Okay, so this is scary. We're going to do an example real quick, though. Not real quick, but in a second. That's going to help sort of, I think, help this. Again, what's the intuition for this? The intuition for this is as follows. In the one-dimensional case, we know that the dx is related to du by multiplying it by something, maybe a constant, maybe an expression. And so if we need a generalization of that, we have to incorporate at minimum 4 partial derivatives. Now we also want to define this in a way so that if we actually just have one variable x instead of x and y, that this thing would just reduce to what we had before. And in fact, this will. So that's another way to think about that. Okay, so and so what is the big theorem going to say? It will say the following. It will say dx dy has the following result. So keep in mind, we already know what happens in polar. It's r dr d theta. Okay, so what would we expect this to be? We expect this to be nothing more than j du dv. So I forgot to write this with the big theorem. So again, if you want to know the technical details of this, there's plenty of places to learn it, but Calc 3, in my opinion, is not one of them. I want you to be able to use this. So let's just check that this makes sense in what we already know. So example, let x equal r cos theta, y equal r sine theta. So that was how we were moving variables. So let's compute some partials. What's the partial of x with respect to r? Well, that's just cosine theta. What's the partial of x with respect to theta? Well, that's a negative r sine theta. And then what's the partial of y with respect to r? That's sine theta. And then what's the partial of y with respect to theta? Well, that's going to be r cosine theta. And so we can compute what is j. Well, j is going to be partial of x with respect to r, partial of x with respect to the second variable, which is theta, and then partial of y with respect to r, partial of y with respect to theta. And so that gives you r cosine squared. Remember, the determinant is you take the diagonals and then minus the product of the other diagonals, and this becomes plus r sine squared. And of course, this adds up to r. And so what we know is, hence, dx dy is r dr d theta. Yikes. Does anybody have a question about this? Comment? For those of you who know a little bit about matrix theory, you'll know that sometimes a matrix has what's called an inverse matrix, and the inverse matrix is very much related to this. The idea of, and even some more fancy notation, I don't know if some of you might be familiar with things like a invertible transformation. And if you do, then it might be a little easier for you to see how some of this stuff sort of plays out. I'm not going to lie to you and tell you that this stuff is easy, because it's just not. It's a complicated thing we're dealing with. And, you know, again, it's tough for me as the instructor to figure out how much of this we should sort of do this explicit details versus, hey, let's just think about dx dy equals something times du dv or dr d theta. It doesn't matter what letters you use, by the way. So some more motivation for J, and then we're going to be done. So suppose we just have some map, which I'll call T, and it takes R2 into some other point. So that just means that T of x comma y equals some function which we'll call h, or excuse me, I'll use g of x comma y, and some other function x comma y. So now this is an interesting thing for us. We haven't done this yet. We haven't talked about a function that has multiple inputs and multiple outputs. We've had one input to multiple outputs, and we've had multiple inputs to one output, but we've never had this. Can we define the derivative of t? So if you bear with me for a couple more seconds, and we're going to be done, but it turns out we can. In some situations, and when we can, it is convenient to write it as a matrix. Now look at what t is. What is t? It has two functions, so it's convenient to write it, and this is just what we did. It's convenient to write it as a matrix, and you take the first function and do the partial with respect to x and then y, and then take the second function, and that is the derivative. So if you think about this, and I'm not saying it's easy, but if you think about it, you'll start to see the analogy between the du equals blah dx. So we're not going to do anything more with this in this class because it's too advanced. And that's not a knock on you guys. It's just Calc 3 is not the place for it. But now I hope maybe you'll see sort of the connection a little, maybe, I don't want to say clearer, but it might help you see the connection between jumping from one dimension substitution to this in 2 dimension. And then if you're brave, you can even do this in 3 dimensions. And we already did it twice with spherical and cylindrical, although we didn't really tell you that, but that's what we're doing. And then you could do this in 20 dimensions if you wanted. Obviously, the notation becomes really overwhelming. And as I said for you, there's a place to study this in more depth. It's called differential geometry, and that is above the pay grade of Calc 3. Anyhow, if you're interested in it and you want to learn relativity and all that crazy physics one day, there you go. Anyhow, do you guys have questions? All right, so think about this if you will. We'll probably give you 1 or 2 practice problems with this change of variables, but we're not going to do too much with it. Maybe we'll give you one famous example, and that's about it. So if you guys don't have questions, I am going to stop recording. I'll save the whiteboards. Does anybody have a question?